So this is the problem we were working on at the end of class on Friday, where I then asked you to use the extended version of the Euclidean algorithm to find the Bézier coefficients. So we start by rewriting everything to get the remainders and then working our remainders backwards. So there's the first remainder. 1 is 16 minus 3 5s. But then 3 is the remainder, so I replace it. And I keep going until I end up with 2 32s and 89s instead of any other numbers way down here. And lo and behold, the number next to my 89 is a 73. And that means that the multiplicative inverse of 89 in the mod 232 universe is 73. By the way, if you get a negative number when you do that, that's okay. But you should find the positive one by asking me what's the smallest positive integer congruent to the negative result you got. You usually just add the modulus to get that one. So this is how we find the inverse. So effing what? Now that I have it, what do I do with it? Now that I have that inverse, I can solve linear congruences like this. On Friday, we just tried one after the other until we found a number that worked. I don't want to try all 232 numbers that are available to me. I'd be here forever. But since I know that the way to undo an 89 is with a 73, I can simply multiply both sides by the inverse. We would have multiplied by 1/2 because it was the inverse of 2, solving 2x equals 7. But here, I have to do that inverse in the mod 232 universe. So I really just have to multiply both sides by 73. So 73 times 89x is congruent to 73 times 15 mod 232. But on the left, because it's an inverse, 73 times 89 is 1. What's 73 times 15? But I want to do this mod 232. So divide by 232 and give me the remainder. Now, really, that means that any number congruent to 167 works. So there are technically infinitely many solutions to this, but this is the smallest positive solution. Let's check. What's 89 times 167? And when I take that mod 232, if it isn't, I have a problem, right? Divide by 232, take the fractional part, remultiply by 232, and there's the 15 I wanted. So this is a solution to 89x is congruent to 15 mod 232. It solves the equation we want. Questions? As I said to you on Friday, this is how public key cryptography works. You distribute the public key. They use that to encode the message. They send you the message. You decode it with your private key. Now, in this case, these numbers are fairly small. So working this out isn't tedious. I mean, as long as you realize that that's the tedious part of it, the Bézier coefficients. But the extended Euclidean algorithm can be coded in a number of different ways. On our web links section on our Canvas page, I put a link to a free textbook section called Blankenship's method. Blankenship's method is another version of implementing the Euclidean algorithm, the extended version, using matrices. My problem with this method is that you're still doing all the same division. You're still working out what changes to make. Here's an example. I want to find the greatest common divisor of 35 and 15. You and I know these numbers are small enough. Greatest common divisor of 35 and 15 is 5. But if I were doing the Euclidean algorithm, I'd say here, do the division, quotient, remainder, and then I'd say 15 is 3 5s with nothing left over. My greatest common divisor must be 5. And then I'd go back and I'd say, oh, so 35 minus 215. My Bézier coefficients are 1 and -2. But what they do is they say, write out a little matrix here. Big number on top, small number on bottom. And then write 1, 0, 0, 1 next. And now you're going to repeatedly add one multiple of a row to the other. That quotient is a 2. So take -2 times the small row and add it to the big row. See the -2? But now this is the big row. So I divide. 15 divided by 5 is 3. Add -3 times this row to this one. And there are your Bézier coefficients. 1 times the big number, -2 times the small number. And I said, sure. So I sat down with our example. And I'm just doing division, right? We said 232 was 289 with a 54 left over. So I multiplied that smaller row by -2 and add it to the first row. And I write the results in the top row. That's what this little legend means here. Hey, there's my 89, my 54, right? That would have been my next quotient division. So 89 is 154 with 35 left over. Take 1 times the small one, -1, and add it to the big one. And I kept going. And eventually, what do I end up with? The greatest common divisor is 1. There's my -28, there's my 73. And those were the numbers we got when we worked out the extended Euclidean algorithm. Not only is this relatively easy to code, I left on our Canvas page a link to an implementation. So if you want to make this code for yourself, you can. As a matter of fact, you can code it in a lot of things. There's my extended Euclidean algorithm coded on the calculator. See the USB port? This is shareable and downloadable because it's already out there on the internet. TI makes a software sharing package. I will post this example as well in Blankenship's method to our notes. Questions? Solving linear equations in and of themselves, while interesting, isn't the be all and end all I want it to be. What I'm really more interested in is solving multiple equations at the same time. The following puzzle is about 1,800 years old. As I am carrying my basket of eggs to market, I spill them. When I pick them up 3 at a time, my last handful contains 2. When I pick them up 5 at a time, my last handful contains 3. When I pick them up 7 at a time, my last handful contains 2. How many eggs do I have? Whatever number of eggs I have is congruent to 2 mod 3. And also congruent to 3 mod 5, and also congruent to 2 mod 7. I want one number that does all of this. Now, you could go through this by blunt force. Hopefully this is not like 3,800 eggs or something. But I'll be here for a while, wouldn't I? There are 2 different methods available for us to solve this. The first is where this problem originates. This is from a Chinese mathematics text written sometime in the early 500s. And the method for solving this is actually constructive. It's called the Chinese remainder. But in order to do this, something important has to happen with all of my moduli. You'll notice that the m's I am using here, 3, 5, and 7, they're all prime. That's not actually a requirement. I just need them to be relatively prime to one another. So my moduli, M1 through Mn, are pairwise relatively prime. Means the greatest common factor, greatest common divisor of any 2 of them is 1. And then we're going to let A1, A2, all the way up to AN just be integers. And we want to solve X is congruent to A1 mod M1. X is congruent to A2 mod M2, all the way down to X is congruent to AN mod MN. This must have a unique solution mod m, where m is the product of all of those little mi's. So I'm going to take all of those numbers and multiply them together. In our case, that's 3 times 5 times 7. What's 3 times 5 times 7? You all own a calculator. It's sitting in front of you. Don't do this in your head. Don't hurt yourself like that. 105. So I'm claiming that the number of eggs I have is less than 105. Now, the proof in the textbook on page 294 is actually a constructive proof. I'm going to build the solution. So I'm going to do this for our example and then show you how this generalizes. For our example, m, 3 times 5 times 7, you said was 105. I need you to compute for me three new values. And those three values divide out the first, second, and third primes respectively. So, in our case, this is 105 divided by 3. This is 105 divided by 5. This is 105 divided by 7. Give me the numbers. Right, if this is 3 times 5 times 7, when I divide it by 3, that's just 5 times 7. That's just 3 times 7, and that's 3 times 5. Now, here's the interesting part. Remember, I was looking at x is congruent to 2 mod 3, right? So this first equation with A1 and M1, wait a minute, 35 and 3, those are relatively prime. The second equation was mod 5. Those are relatively prime. The third equation was mod 7, and those are relatively prime. Why do I care? Because it means any equation 35 something in mod 3 is going to have an inverse. Any equation 21 something in mod 5 is going to have an inverse. Any equation 15 mod something in mod 7 is going to have an inverse. These all satisfy the previous extended Euclidean algorithm idea. All right, wait a minute. I want to find the inverse of these numbers mod these numbers. So I need to know 35 something is congruent to 1 mod 3. I need to solve for that y. Over here, 21y2 congruent to 1 mod 5. And over here, 15y3 congruent to 1 mod 7. Now I have a distinct advantage. If I'm working mod 3, like I'm in this first equation, then I don't need the number 35. I should take the remainder, mod 3. What's 35 mod 3? So really, I want to solve this equation. What do I want to do here? Say again. That's the quotient. What's the remainder? 21 mod 5 is just 1. Mod 7. 15 mod 7 is also 1. Hey, wait a minute. That means that one's solved and that one's solved. 1 y2 is equal to 1. Therefore, y2 is 1. Same thing with y3. y1. If I'm working mod 3, then the only numbers I care about are 0, 1, and 2. I can just check by hand. Can y1 be 0? 2 times 0 is definitely not 1. How about 1? No, because 2 times 1 is 2. Mod 3, but 2 times 2 is 4. Mod 3, that's equal to 1. So I actually have all 3 values. Now, my value for x. You take the capital M's that you came up with in each statement. You multiply it by the y that you came up with in each statement. You then multiply by the a you came up with at each section. So the a was given to me in the original problem. The original problem said x was congruent to what mod 3? It was 2. So 2 times 35 times 2. That's the y for that part. Plus what was the mod 5 part? And the mod 7 part? Multiply and add, people, give me a number. But that's a lot of eggs. Remember, we are working in a modulus. There is a unique solution mod little m. What was little m for our problem? There it is. 105. How many eggs? If you pick them up 3 at a time, you pick up 21, your last handful is 2. If you pick them up 5 at a time, you pick up 20, your last handful is 3. If you pick them up 7 at a time, you pick up 21, your last handful is 2. I will tell you right now, I hate this theorem. Because it requires me to construct all these things, and when I try and read the proof doesn't actually tell me why these are the things you want to construct. So as much as I like the fact that this gave me the right answer, and it did it relatively smoothly, I don't actually like solving this idea this way. I'm much happier using a different process called back substitution. Now, I'm pretty sure You've heard that phrase before. Where have you heard the phrase back substitution before? At least you should have heard the phrase before. I hope not. What was that, Roman? I've seen this phrase when solving simultaneous equations, right? When you've got like x plus y equals 7 and 2x minus y equals 2, and you've got to figure out what x and y are, you solve for one of them, and then you back substitute to solve for the other one. When you had 3 equations and 3 variables, the same idea. You would solve for one, then you would go back and solve, and then you would go back and solve again. Triangular systems of equations, one in x and y and z, one in just y and z, one in just z. You're looking at me like I'm a space alien. Chapter 9 of the algebra book we use here. It's in the math center. But if that's my goal, what I'm actually going to do is try and solve these equations one at a time. And when I come up with a solution for the first one, I'm going to put that into the second one. Wait a minute. Oh, and then eventually I'll put it into the third one. Congruence to 2 mod 7. All right, let me start at the top. If x is congruent to 2 mod 3, anything that's congruent to 2 mod 3 means that I can write it as 3 somethings with 2 left over. And all I know about k is an integer. Now, the Chinese mathematicians, the Egyptian mathematicians, Babylonian mathematicians, a lot of mathematicians before about 800 AD didn't like negative numbers. So the assumption here is all of these numbers are positive. Now I'm going to take this expression and substitute it in here. Here's my back substitution. Let's solve that. I subtract 2 from both sides. I get 3k is congruent to 1 mod 5. But notice 3 and 5 are relatively prime, aren't they? That means that 3 has an inverse. We're working mod 5. My numbers are small. I can check it directly. If my numbers were big, I'd have to go through the extended Euclidean algorithm to do this. But my numbers are small. What is the inverse of 3 mod 5? What solves this equation? K is equal to 2. Because 3 times 2 is 6. That's congruent to 1 mod 5. Wait a minute. If k is congruent to 2 mod 5, that means that k can be written as what? Yeah, I already know that x is 2 mod 3. I don't know that k is 2 mod 3. But I do know that k has a writing mod 5. How can I write k from this equation? Very much like what I did right here. It'll be 5 something plus 2. And all I know about the something is that it's an integer. With me so far? It's weird, but I get it. Let's put those two together. So far, so good? Now let's go to our third equation. If I am working mod 7, then any number bigger than 7 should go away and be replaced with its remainder, mod 7. So I have a 15 and an 8. Blow them up. What happens? Do those mod 7.
15 2 mod 1.
I need one number, which is the mod, which is the div, quotient or remainder. Important to tell these apart. I want the remainder when you divide by 7. 15 divided by 7 is 2 with 1 left over. Just the remainder. I don't want the quotient. Perfect. Wait a minute. If that's the case, what's t? T's just 1. What's x? 15 times 1 plus 8 is 23. Oof. Back substitution is much faster when I can work with small moduli to find the inverse. If this is a larger process with larger numbers, then the Chinese remainder theorem version is probably much faster. Because the proof is constructive, I can actually feed you all the numbers and just say, do the right multiplication, do the right division, and we're done. But there's a lot of, where's the Bézout coefficient? Where's my inverse come from? We did all that by hand. I would have to do greatest common divisor through the extended Euclidean algorithm multiple times. Did I have to do any of that here? I got really, really lucky. Why? Because I was solving very small congruence relationships, and I could do those by hand. For most of the problems we're going to attack in this course, back substitution will probably be better. For most of the real applications we're going to do, like hashing algorithms, I'm going to code this sucker to do the inverses and Blankenship's method directly. I'm not going to do a bit of this by hand. Multiple key hashes are exactly this sort of idea. Do your check digit, your check bit, based on several different moduli. You've confirmed that you have the correct information as long as all your check bits match. But now you have multiple check bits to pick from. Gee, I don't know anywhere we use this idea. Do you? The last number in an ISBN is a check digit. It's based on the hash of the others. The security code CVV on the back of your card is a hash bit. Useless stuff. We're never going to use this. Questions? Example 8, page 279 to 280, goes through calculating large prime numbers, large powers of prime numbers. And it's much easier to do these in terms of their moduli to relatively prime integers, just like we did our modular exponentiation. If I'm doing large products, this will come in very helpful. But this is not terribly old math. I mean, the Chinese remainder theorem itself is not new. It was known way back. But the applications of it are fairly modern and were, up until the 1900s, assumed to be impractical in terms of computation. They just took too damn long. And now you have something sitting in front of you that does billions of computations a second. That's much faster. But when it comes to doing large primes, the ideas are not new. Normally, when I say Fermat, I think of Fermat's last theorem. Anybody know Fermat's last theorem? For any values A, B, and C in the integers. Not only for cubes, but for every power bigger than 2. A to the n plus B to the n can never be C to the n with A, B, C integers and an integer bigger than 2. It just doesn't work, period. In the process of trying to show that, by the way, Fermat actually wrote in the margin of his book, I have a lovely demonstration of this. It's too big to fit in the margin. When translated into English, it was translated as I have a lovely proof of this. We have no idea if Fermat actually proved this or not. But a guy by the name of Andrew Wiles actually did in the early part of this century, 300 years later. But in the process, Fermat was starting to think about prime numbers and powers of prime numbers, right? Because we want A to the n, B to the n, C to the n. Fermat showed the following. That's an A. If I have a prime number and I have a number that doesn't divide it, that means that number is not 1 and not P itself, or any multiple of P, then A raised to the P minus 1 power mod P is 1. And A to the P is A. For every possible value A that doesn't divide the primes. How is this going to help me? Remember, for our modular exponents, we were taking very, very large powers. I would like you to compute 7 raised to the 121st power mod 13. You are not permitted to use your calculator for this problem. We're going to be here never, are we? We could do the modular exponential, right? I need the binary expansion of 121, and I need to know that whole algorithm by heart. No, no, no. Fermat allows me to cheat. Because what Fermat's theorem says to me, wait a minute, I'm working mod 13. That's my prime. So every time I raise 7 to the 12th power, I get 1. Wow. Why is this helpful? Quotient remainder, please. Told you we were going to do a lot of this. So when I do 7 to the 121st, I'm really doing 7 to the 12 times 10 plus 1. When you're adding powers, that's the same thing as multiplying. So this is really 7 to the 12 times 10 times 7 to the first. When I am multiplying powers, I'm really doing a power of a power. So I'm going to write this as 7 to the 12 to the 10 times 7 to the first. I want to apply mod 13. Means I want to apply mod 13. And if I apply mod 13, I can apply it to each part. And every time I do 7 to the 12th, I get a 1. What's 1 raised to any power? I'm done. The answer to this problem is 7. As long as my modulus is a prime, raising to particularly large powers becomes a matter of raising to the remainder of that power. So if I want to check for crackable codes with my modular exponentials, I'll look at the result of my ciphertext mod P. For P, a reasonably sized prime. The RSA knapsack cipher is crackable. It's not reasonably time-wise crackable. It's really very complicated to crack. But that's a method to approach that cracking. The problem is when my power is still smaller than my modulus. If I was, instead of working mod 13, if I was working mod 101, I might have a bigger problem here. I was raising like 7 to the 98th mod 101, because I wouldn't be able to use the division that I used here to simplify my process. Questions? When Fermat put this together, he was only looking at what happens when your modulus is a prime. Leonhard Euler came along and said, hey, what if your modulus isn't a prime? What Euler noticed is that if you think about all the numbers less than a prime, all of these, the greatest common divisor with the prime is 1. So all of these are relatively prime P. But if you're dealing with a number that isn't prime, then only some of those numbers will be relatively prime. Six is not prime. Which of the numbers less than 6 are relatively prime to 6? Two and 3, the greatest common divisor of 2 and 6 is 2. Greatest common divisor of 3 and 6 is 3. Greatest common divisor of 4 and 6 is 2. I want the ones where the greatest common divisor is 1. The only ones that are relatively prime are 1 and 5. Same question. Which numbers are relatively prime to 8? Right? Greatest common divisor of all the rest of them is 2. Euler decided on a function, and he was going to call it phi of n. And phi of n counts how many numbers less than n are relatively prime to n. So what we've just shown is that phi of 6 is 2, and that phi of 8 is 4. And this one up here shows that phi of p for any prime number is p minus 1. Euler was able to generalize Fermat's little theorem. As long as A does not divide P. If I'm working mod 6, I'm really only working with 1 or 5. What's 5 raised to the second power? Mod 6. You got your calculators. What is 7 to the 4th? Mod 8. The quotient is 300. The remainder is 1. Proving this requires me to do a lot of work in Zn. And that proof can actually be found in the abstract algebra course, SMA205. Not here. But it has to do with the way in which the set of numbers Zn works. I'm done talking about number theory in general. If you want to know more about the specifics of cryptography and cryptanalysis, you should read the next 2 sections in chapter 4. They go through the entire RSA knapsack ciphering procedure and give you quite a bit of basic cybersecurity information. That means I'm going to move to the next chapter, which is about a new method of proof. So I'm going to start doing proofs again, Don't run screaming for the hills, these are useful. This is the basis for recursion. I will see you all on Wednesday. Have a wonderful rest of your day. If you came in late and I still have your homework, come get it.